Good afternoon, and welcome to another Research in Action brought to you by the Division of Research at Florida Atlantic University. With that, it is my great pleasure to introduce today's speaker, Dr. Feng-Hao Liu. As you all know, and you may actually have encountered it, is the hacking and the cybersecurity that is getting more and more important in our more and more digital and electronic world. And Dr. Liu's research is somewhat in that area. So Dr. Liu is currently an assistant professor here at Florida Atlantic University and hails to us from Maryland, University of Maryland, where he has done a postdoc experience, and before that he received his PhD at Brown University. His expertise is in cryptography, and particularly post-quantum cryptography. And I hope he will tell you himself now what that actually means. Welcome, Dr. Liu.
Thank you for the introduction. So the topic today I'm going to talk about is next generation of information security. And this contains some interesting work I have done in recent years. So we start with the picture for security demand for the future. This is motivated by the Internet of Things. We know that more and more devices are going to be connected, and the user might have multiple devices and perhaps a very large data. And instead of storing her data locally among multiple devices maintaining copies, she might outsource the data to the cloud. And later on, maybe she would request access or compute on the data. And this paradigm is very convenient for users to access or share the data. And it also can reduce the cost of maintaining large data storage infrastructure. However, there are potential risks in this picture. We know that data might contain sensitive information about individuals, business, and organizations, such as your private photos, emails, or credit card information, or your medical data. Okay. So we have seen a lot of information leakage and data loss or integrity breach in this picture in the news, in the press, or in many, many different places. We know the consequences are huge, and we recall several very famous instances. In 2014, Apple iCloud had this very big data breach, which leaked a lot of celebrities' photos. And that was pretty annoying at that time. And in the same year, the Home Depot had a very big data breach. And the instance leaks a lot of users' credit card information stolen. So yeah, it causes a very big amount of money for Home Depot to settle. And of course, many banks need to reissue their credit cards, so it's quite like a very annoying. And very recently, in a news saying that therapy records were stolen by hackers, and later on, some patients were even blackmailed, and this just happened maybe late October and in Finland. So we know that cryptography is a very important foundation to protect Internet of Things. And based on these instances and example, we know that the current methods do not really provide sufficient security guarantees. So we need to rethink a little bit about like the underlying crypto methods. And particularly, if we look at the traditional cryptography, basically it focuses on protecting communications like this picture. And outside this picture, we know that there could be many, many empty spaces there, so that this would open many more places for the attacker to attack. For example, he could break into the cloud, or he could attack implementations. And even worse, the attacker might have more powerful attacks. So researchers are worried about what if the attacker has access to quantum computers, And this would become a very devastating threat to the current crypto infrastructure. So we know that back to the Second World War, the traditional computers, like those pictures, they have played an important role in breaking the crypto system in use. And after decades of research, scientists have already identified many new candidates, such as RSA crypto systems, where traditional computers cannot break. But yeah, it has been proved that quantum computers can break all currently in use crypto systems. Yeah, so the thing is, even though large-scale quantum computers haven't been fully realized, there has been tremendous progress for the state of the art, at least in the labs. So due to, if we really want to compare the power of the computational power of a quantum computer versus traditional computers in breaking crypto systems, then the traditional computers can be thought as this cannon, and the quantum computers can be thought as this Death Star. So even though it hasn't been fully built yet, yeah, researchers need to be proactive, right? Because we cannot wait until that day when he shows the weapon. Okay, so the mission in summary, to secure the future, we want to build a new shield that secure implementation and the cloud, and also it is quantum resilient. And this is a very important task towards realizing a secure and trustworthy cyberspace where many applications can build on. And it is also necessary to protect fundamental human rights of data privacy, so that so our data privacy will not be compromised with the growth of technology. They can grow together. This is very important. Okay, so yeah, during the past couple of years, or maybe past 10 years, I have been studying those three areas: how to secure implementation, the cloud, and quantum resilient. And instead of talking about like one particular technique or one particular subject, my intention here is to talk about how crypto can connect those seemingly different areas. So as long as we are good in foundation, then we can like make contributions in many different subjects, because they are all connected. Yeah, as long as we see them in the right way. All right. So let's talk about the first direction, how to secure implementations. So the motivation of this is, we know that crypto systems are severely challenged by attacks on implementations known as physical attacks. Generally, they can be categorized by leakage or tampering attacks. So we have seen that in experiments, researchers know how to crack the RSA systems by using, say, a combination of these attacks. And those results were back to 2000, early 2000 to 2000, say 10. We already know those attacks in the lab, at least. So those attacks, they do not attack the underlying underlying mathematics, but they kind of like in another way, they bypass the underlying mathematical hard problem, but just attack the implementation, so that if your hardware doesn't carry out like a perfect and secure implementation, then it's possible the scheme is vulnerable. Okay, and also it has been shown that physical attacks can be general, not designed specifically to a particular crypto system such as RSA. So in a celebrated result called a code boot attack, it has been shown that attacker can possibly steal some of your secrets stored in the memory if your device or computer falls into his hand. So at a high level, the attacker is going to freeze the memory so that the content fades away slowly when detached. And so by doing so, if say your computer falls into his hand, he can freeze the memory first and then unplug the memory from your device and read the memory in his device. And so it has been shown that like in this picture, you can see like in the left-hand side, the memory content fades away very, very slowly. So it's possible that the attacker can obtain a significant leakage of the memory content. So all those examples show that physical attacks are possible. And so in order to meet future security demands, we must deal with physical attacks. So a very, very interesting tool to secure implementation is called non-malleable code, originally proposed by 3 researchers, Dembowski, Piachak, and Weeks, back to 2010. And interestingly, that paper was first published in a very new conference at that time called Innovation in Theoretical Computer Science. And later on, this tool has been significantly explored. And later on, they submitted, the authors submitted their paper to a journal called the Journal of the ACM, which is the top journal of computer science. And their paper got accepted. So it is very interesting. So it's interesting that their paper got accepted into the top journal, and yeah, showing that the significance of this technical tool. So the idea is very simple. So you encode the data such that it is tamper resilient. So what is tamper resilient? By to capture this, I use the following animation, and hopefully, yeah, it makes sense. So you have a data, and so the encoding non-malleable code encodes this data into some kind of structure. And by tampering with the data, it can only result into 2 cases. So either you keep the data unchanged, or you completely destroy the data. So this means that the code word becomes something encoding of an unrelated message R prime. So this non-malleable code offers a very simple and elegant paradigm to protect data against tampering attack. Instead of storing the data in the clear, you just store an encoded version of the data. Okay, so now the next question is how to construct such a code. And we first notice that the non-malleable codes cannot exist against all polynomial time functions. And this is because if the tampering function can decode and then re-encode, it can certainly create related encoded message. So this notion against all tampering functions is not achievable. So at that time, researchers spent a lot of time identifying what results are meaningful and what function class are feasible for non-malleable code. And in my very early work, I developed a new code. I identified an important class called the split state model, where the adversary can only tamper locally. What does this mean? So yeah, before I explain further, let's consider this idea that memories are placed physically far apart such that attacks cannot be applied to the components jointly. So why memories are placed physically far apart? If you open, say, if you have like opened your desktop back to say 2010 or 2012 at that time, so it looks like something on the right. So we have several memory slots, and you place different memories like in different slots. So intuitively, they are physically far apart. And I kind of explore this intuition, saying like, okay, So suppose your adversary can attack on each piece of the memories, but not jointly, then maybe we can design such a non-malleable code. So the goal is to say encode messages into say at least 2 split memories, such that if the attacker can tamper on those 2 memories locally, then he is not going to break security because of the non-malleable code. So by tampering, he can only either keep the data unchanged or otherwise completely destroys the data. Okay, so my work during that time, that was my PhD time, I construct the first code of this class. And moreover, I add leakage resilience to the code, meaning that if the adversary can get partial leakage from the code word from 2 pieces of the memory, he can still not break the code. And one very important feature is I prove tamper resilient via leakage resilient techniques. So this is very interesting because we can think of tamper resilient as a more active attack where the attacker can perform some active write attack by changing the memory, and leakage resilient can be think of say the attacker is going to perform some passive attacks. So here, the overall concept of this result is we know the conceptual message is don't place all your eggs in the same basket. So suppose we place our secret data into 2 pieces of memories, then it is possible to achieve very strong resilience to tampering and leakage attacks. And the second conceptual message is actually leakage resilience is a very, very important foundation because it can help us to achieve further tamper resilience. Okay, so I graduated with this result writing a very beautiful paper published at a top conference called Crypto. And then, yeah, I was very happy. But after graduate, I kind of got several interesting questions by saying like, who cares about those results? Are those a little bit too theoretical or something like this? And yeah, and recently, maybe not so recently, but back to 2016, I found a great motivation from NIST. So NIST stands for National Institute of Standards and Technology. So back to 2016 February, they had this call for new post-quantum crypto standardization. So yeah, I will certainly talk about this PQC standardization later. But in this call, they request for new crypto standards to replace the current one. And one very important feature of the call is they request the new designs to be resilient to side channel attacks. And side channel attacks are a special type of leakage attack. So this means physical attacks are very, very important. And we all know that this new standard, say after say a scheme is selected, will be widely deployed almost in every new computer systems. So the current research effort will be very, very influential for our future computer systems and future cryptography in use. Okay, so with this great motivation in mind, then I look at another drawback of my previous scheme. So my previous construction, the efficiency actually is not very good. So what if your construction, the efficiency is not good? It's not, actually, this is not really a bad thing because this opens a room for you to improve. So the idea is, yeah, to improve a construction, we need to identify the bottleneck of efficiency. So after a careful look at my construction, I found that my construction uses a encryption scheme that and a key stored in the memory. And then here, I require a very special cryptographic primitive called non-robust, non-interactive zero-knowledge proof. Without talking about what it is, we notice that this is really a heavy machinery. And this heavy machinery will kill the efficiency. So this is basically my construction. And so with this thing in mind, how do I deal with this efficiency? So my idea is I want to replace the inefficient cryptographic primitive with some lightweight hash. So the constructions would look like this. And of course, for crypto designs, if we want to compose combine several, let's say, encryption with a hash, usually you really need to do a formal proof of security. Otherwise, how can you show that the combination is secure as well? And yeah, and I have already noticed that not all hash suffices for the construction and for the proof of security. So we need to identify what cryptographic properties do we need. And in a later work, I identify a new hash function called one more extractable hash. And this is a new notion, and I can efficiently construct this new notion from some group assumptions, and it has a very deep connection with leakage resilient technique again. So at a high level, so I have a new notion, new theory, new implementation, a new instantiation, and new conceptual message. So before writing a paper, what is the logical step to do? And of course, it should be write a proposal first, and then hopefully it is going to be funded. And I was very lucky in this perspective because I first wrote a proposal, and then I got funded. My first award from NSF is an initiative award. And then I got a paper accepted to a very top security conference called CCS. So yeah, but of course your research won't stop after you get an award. So if we get an award, so what should we do next? So of course, is we want to explore more. So, so the techniques from split state model actually enables new constructions for further classes. So one particular class I achieved is called partial functions. So what is partial function? So you can encode the data into code word such that the attacker can read or write at a very large fraction of the code word, something like this. And this fraction can be anything as long as it doesn't read everything. Okay, so he can choose any large subset to attack. And yeah, but even if he can do so, he cannot break security. And this result kind of generalized a prior notion called all or nothing transform, which is exactly the same thing, but only protects passive read. And this notion was proposed by my great advisor, Ron Rivas. Yeah, you might have all heard about Ron Rivas because he is the R in the RSA. Yeah, RSA is the very, very famous crypto system in use. Yeah, so yeah, and RSA is named after three researchers, Rivas, Shamir, and Edelman. And yeah, so my great advisor is Rivas. Okay, anyway, so so now we know this is the first direction I'm going to, yeah, I have done. And now I'm going to talk about the second direction, which is how to secure the cloud. Okay, so one very important technique to secure the cloud is fully homomorphic encryption. So what is fully homomorphic encryption? Intuitively, if you have a, say, encryption of X and a function of F, fully homomorphic encryption allows you to compute F of X encrypted, even without decrypting. Okay, and this idea is very important, and it has been first realized by Gentry back to 2009 for general functions. By general functions, it means F can be any polynomial time computable function. Okay, and the idea can be generalized to homomorphic computation, which has been demonstrated useful in constructing other advanced crypto systems such as identity-based encryption, attribute-based encryption, and many, many other things. All right. And there have been many follow-ups of this technique. And initially, the construction of Gentry 09 was considerably inefficient in practice. But after, say, 10 years of research, there has been a lot of progress in like making some of the computation much more efficient. So now you cannot just say, okay, if anyone is using FHE, it's going to be inefficient. This is not the case anymore. Yeah, of course, there are some computations that are not efficient, but yeah, there are also other important computations that can be done efficiently. Okay, so how do we use FHE to protect data in the cloud? So before outsourcing the data, the user can just encrypt the data and just send the encrypted data to the cloud. And later on, when she requests a computation, say some F, perhaps like search of the email or do some kind of learning algorithm on the data, then the cloud can compute F of the data encrypted. And so in this case, the cloud still doesn't know what the data is, but can provide meaningful functionality over the data. So this is a very significant result in theory, and there have been a lot of more practical scenarios implemented using this technique. Okay, so my early research about fully homomorphic encryption actually is very simple. So the question I asked was, can FHE be leakage resilient? Which means the scheme remains secure even if some partial key is leaked. So in my earlier work, I created the first leakage resilient FHE. And there is a connection between analytical techniques in lattice-based cryptography, which is the next subject I'm going to talk about, but this is very important. So this shows how to FHE, how to secure the cloud and how to secure implementation. They have some kind of a connection. And at that moment, I really didn't know what else I can do with this result. I have a very nice analytical technique, math, but I just couldn't figure out the applications. I mean, other applications than leakage resilient FHE. But anyway, I have had this nice idea and technique planted in my mind, and hopefully we will see. Okay, so the next research I'm going to talk about is can FHE be distributive? So what does it mean by distributive? So the first thing is we want distributive public key generation. So instead of generating the public key by a central party, we want every party, say for multiple parties to contribute the public key generation. And later on, given this public key, each party can compute on ciphertext from all different parties. So what does this mean? This means so those parties, they can encrypt, say, their inputs X, Y, Z, and without interaction. And later on, after publishing those ciphertexts, they can compute on a joint function f of X, Y, Z on those ciphertexts. And then after this step, I want distributed distributive description. So this means everyone given this C star can compute a share of the underlying message of f of x, y, z. And so each individual share cannot like decrypt. But suppose we have collected a sufficiently many shares, then we can decrypt. So this is called threshold decryption. And the next interesting question is, why do we want to make FHE distributive? And of course, at that time of the research, blockchain was not that hot at that time. But now we kind of have an idea that we want to decentralize the trust. So we don't hope, like say, public key is only generated by a single party, and or we want like to decentralize the trust a little bit. But there is even before the motivation by blockchain, there is still a very, very fundamental motivation called multi-party computation. So distributive FHE would imply multi-party computation. So what is multi-party computation? This is, say, we have, say, those three parties and the cloud. And those three parties and the cloud, they want to run a protocol to emulate an imaginary trusted entity holding a general function f. And this imaginary party will collect in private inputs from the users and send the computation of f of x, y, z to the cloud. And if so why do I say emulate this trusted entity? This is because by emulation this securely, this means the cloud can only learn f of x, y, z in the protocol, but nothing more. He cannot learn the private inputs x, y, z from the users. And moreover, the distributive FHE will achieve something stronger called guarantee of output delivery. And also this is round optimal, so 3 rounds for general functions. And so what does that mean by guarantee of output delivery? So this means even if some parties drop out during the computation, it will not block the delivery of the output to the cloud. Okay, so what is round optimal? So round optimal means like 3 rounds are possible, but not 2 rounds. So this means 3 is the optimal. So how to achieve 3-round protocol? So intuitively, the protocol has very simple structure. So in the first round, parties do this distributive key generation, and then they encrypt their input, and then they do the evaluation and threshold decryption. Okay, and in this work, back to 2015, we also showed that so for some particular functions, it is not possible to achieve an MPC with guarantee of output delivery done in 2 rounds. And this is a very interesting connection. So there is a sharp bound, bound, upper bound and lower bound. So 3 is possible and 2 is not. Okay, good. And I also got several questions about this work. Why do you care about guarantee of output delivery? Is that just because of theoretical interest, or is there a scenario where like we really care about this security property? And at that time, actually, I really didn't know I really didn't have a very good answer for this question. And until very recently, I found like there is a very nice scenario called federated learning, where so in federated learning, there are several parties and they want to contribute some data to the machine learning process done by the cloud. So, and of course, some parties, some devices will drop out due to the poor connection, or maybe the unstable connection. So in this scenario, we really want the cloud to be able to receive the output, even if some devices could drop out. So in that work, this output delivery is very, very important. And of course, in another chance, am very, very happy to talk about the federated learning and multi-party computation. So today I have several other interesting subjects to talk about. So maybe, let's just skip this part. So so from this picture, from the previous examples, we have seen several important applications of homomorphic computation and homomorphic encryption in theory and practice. So the first thing is we know it's connected to leakage resilience and multi-party computation. And leakage resilience is further connected to non-malleable code. And multi-party computation is connected to federated learning, which is another interesting thing for machine learning and AI. So by exploring this picture a little bit more, I identified that homomorphic computation has connections with fine-grained access control, which can be used to achieve better leakage rate and improve leakage resilience. And also, homomorphic computation has nice applications to tighter analysis of cryptographic primitives and better efficiency. So particularly PRF and IDE can be connected, can be improved by using homomorphic computation. So by exploring this net of questions and those research directions, I have successfully obtained the second my award, which will support me to do for this exploration for the next 5 years. And the topic is towards efficient cryptography for next generation applications. And so how to achieve this task is by exploring those fundamental, this net of problems. Okay, so now the second direction, I put a badge there, and now I'm going to move to the third direction. But how are those directions connected? So we first, notice a problem. So before, as I said, homomorphic computation has a lot of applications, but we really want to ask the fundamental question is, how can we improve the foundation of FHE and homomorphic computation? So of course, if we have homomorphic computation, we can do a lot of things as I just described. But the real challenge is, can we also improve homomorphic computation itself? Okay, so not just improve the application, also improve the core of homomorphic computation. And to achieve so, we really need to understand what is the fundamental technique that powers homomorphic computation. And in this case is lattice-based cryptography. And very luckily, lattice-based cryptography is also an important foundation of post-quantum cryptography. So if we can improve lattice-based cryptography, we will improve post-quantum cryptography and homomorphic computation together. So this means we can include all these applications with post-quantum cryptography, which is a very, very good thing. Okay, so this says how to secure the cloud has a very natural connection with how to defend against quantum attacks. So so now I'm going to talk about the third direction. So the fundamental question we are asking is how to secure data against quantum computers, which, as I describe as this Death Star of traditional computers. cryptography. So here I recall the context a little bit more. We all know that currently in use crypto systems can be broken by large-scale quantum computers. And why is that the case? It is because the underlying mathematical foundation can, such as integer factorization, discrete logs, those hard problems can be broken by a very famous algorithm called Shor's algorithm. And so for future security, NIST has this call for standards back to 2016, which requires, say, post-quantum security and efficiency. And we all know that deployment of new standards takes a lot of time. By this NIST report, it almost took us, say, 20 years to deploy the current one. And this is because, like, if we want to change the system, if we want to migrate a system to the next generation, there are a lot of issues. It's not just like I change this system. I also need to have this compatibility issue, right? So maybe perhaps some systems are using old standards and some systems are using new standards. Can you still like guarantee that the transition is smooth? So it's not saying like after a cutoff date, all the old systems are going to be done and you cannot use them. And yeah, this abrupt transition is not something we want. But if we require a smooth transition, then this means taking time. So the idea is we had better to start now. Okay, so how to achieve, say, post-quantum cryptography? There are a lot of, say, maybe not a lot, but a few directions. And the promised direction is lattice-based cryptography. So based on some harness of lattice problems, we can create cryptography. And of course, lattice-based cryptography is not the only one that can achieve post-quantum cryptography. It is one of the very promising candidates. There are some others, for example, like code-based cryptography and isogeny-based cryptography. And some like other cryptographers at FAU, they studied, for example, isogeny-based cryptography or code-based cryptography. So this is not like the only one, but there are some unique features of lattice-based cryptography. So for example, the operations are efficient and it is very plausible to resist quantum attacks. And most importantly, it is a foundation, an important foundation for homomorphic computation and thus all these significant implications. So the idea is the third advantage is really something unique to lattice-based cryptography, not found in any others, such as code-based or isogeny-based cryptography. Because say for researchers, we are not just only focusing on what currently NIST is funding. We want something more. We want something even beyond like NIST's current project. So yeah, in order to achieve something homomorphic computation, FHE, multi-party computation, those tasks, we really need lattice-based cryptography. So this is a very good motivation to study this primitive and this direction. So to study lattice-based cryptography, you need some hard problem to work with, right? So yeah, you need to know like what is the foundation hard problem from lattices, and then from there you can try to construct your crypto systems. And here there is a very famous problem called learning with error, and proposed by Regev back to 2015. And the idea is like something like this. So the problem is you are given a bunch of vectors A1, A2 to AN from some ZQ to the N. And also you are given some inner products of AIs with some secret S and plus noise. And the goal of this problem is you are given those bunch of samples and you want to find S. And how, say, suppose your inner product does not contain noise, then and solving this problem is very easy. You can easily solve the system by solving a linear equation, which can be done in like the basic linear algebra course. But the problem is if the samples contain noise, then the problem becomes significantly harder. And even more, we can show a reduction from some lattice problem to learning with error. So what does reduction mean? This means, if you are not a computer scientist, this is fine. But here, the logical implication is very clear. So the implication is, if the underlying lattice problem is hard for quantum computers, so is learning with error. Okay, so reduction is a very, very important technique to relate two different hard problems. And this is why people call learning with error lattice-based cryptography, although it doesn't look like, but because there is a reduction that connects some lattice problem with learning with error. So now we call it LWE, learning with error, lattice-based cryptography. And as I said, learning with error is is a foundation for more advanced crypto systems. It can be used to build, say, public key encryption signatures and also homomorphic computation at FHE. So it is very important. However, the plain LWE is not efficient. So why is it not efficient? Because usually it requires very large keys and converse and noise sampling procedure. And we noticed that NIST did not select the plain LWE-based solution, called a scheme called Frado as finalist, but just as a backup or alternative. So if you look at the NIST current progress, now the current NIST computation contains rounds. So say in the first round, everyone can submit, and then they select partially, maybe cut it into half to the second round. And now it's third round and it's the final round. So final round, there are 4 candidates in the, for encryption schemes. And 3 of them are based on lattices or different flavors, but they are all lattice-based cryptography. So this means lattice-based cryptography, LWE, is very important. All right, so this is just a very quick update of the current status. So if we look at a picture of, I made an animation. So if plain LWE is not good, efficient, then what do we need? So here the animation says, master, we need new hope. And the master says, more you need Kai or Saber. So if you're familiar with those movies, then you know who those characters are, and you know what New Hope is, and you know what Saber is. But the interesting thing is those candidates and those schemes, they really name their scheme as New Hope and Kyber or Saber. And but before talking about New Hope or those schemes, we need to understand what is the hope. So the hope is we need additional mathematical structures to improve efficiency. So one idea is we use a math structure called rings. So and another thing is we don't generate noise. We use a simpler operation called rounding. So look at this. So instead of generating A1, A2 to AM from ZQ to the N, we generate them from some ring RQ to the K. And instead of using a noise generation, we use just round. Okay. However, this might incur further subtleties, right? So which ring are we going to use and how to round? So there are a couple different selections. And the most fundamental question is, are those variants secure as well? Because the adversary might strike back by exploiting those mathematical structures as well. So now I can give you an update of like another thing about the NIST post-quantum standardization, like some little story. So in the second round, New Hope, they really use they use the idea of working in the rings, and Kyber and Saber, they use different rings and also different, perhaps like Saber uses like rounding. So sometimes like, it is very interesting if you design a scheme and then you want to really give an like a more aggressive name, right? So if you just give the name New Hope, maybe that's not like strong enough. So you want something more like Saber, so that like Luke has better power when he has Saber. Okay, so my contribution in this line is, let's look at some existing harness results for the, so the high level thing is we want to determine whether like working in the rings, whether using rounding will like kill your hardness. So existing results, we have already known that from plain LWE, we have reductions from lattice problems to LWE. And so this means hardness of lattice problem can guarantee hardness of LWE and can further guarantee hardness of learning with rounding and maybe entropic learning with error and rounding. So what is entropic? What does this mean? Entropic means the problem remains hard even if the secret is somewhat leak. And from ring, we only know how to, like from some ideal lattice problems, the hardness there can be transferred to the hardness of ring LWE. But the next question is, can we combine those two techniques and show that hardness of ring LWE are learning with rounding and entropic ring learning with error and rounding? So the question was not clear. So in my very recent work with my postdoc Zedong Wang at Florida Atlantic University, we showed that for some commonly used rings, we can actually achieve this. So it's just saying the result is very simple to state. We are able to combine the two, like the hardness results from the previous like picture. So there is a very new technique, mathematical technique called algebraic randomness extraction, showing that if you have a random A and say some X from some distribution, and inner product of A and X behaves uniformly random if your X modulo every ideal J in the ring has sufficient entropy. Okay, this statement looks a little bit cryptic. And in fact, it is cryptic because of those mathematical structures. But in order to understand these mathematical structures, we really need to go into algebraic number theory. And this algebraic number theory was developed by Richard Dedekind back to like early, late 80s and early 19. So but without knowing what algebraic randomness extraction, this technique is, we just need to notice that it is an important missing link in the ring analysis. Okay, so now I want to give you a taste that why entropic hardness result is something desirable. So
now we only have 2 minutes left.
Okay, so let me finish this in 2 minutes, and actually this is very close to my last slide. So if a scheme or a harness problem is not entropic, not robust, then if say we compare with like a robust scheme, so if there is no leakage in the secret, then both achieve like a full security. But if you leak every bit of your secret, then there is no security. So if a scheme is not robust and not entropic, then maybe such as RSA, if you leak 1/4 of the secret key, then the security goes away. And what about in the middle? Then we don't know. But if a scheme is robust, then the security degrades smoothly with leakage, so that even if your secret is slightly leaked, then yeah, we can still have security guarantee. But this is not true for non-robust harness. So in the future, we definitely want to select something which is robust, and yeah, this will make our implementation much easier. Okay, so finally, I want to say, learning with error and like has really important other important applications. For example, identity-based encryption, functional encryption, and program obfuscation. And yeah, I don't tell you what they are, because maybe I will in the future talk. And post-quantum cryptography has another very interesting application that's very, very connected to the research frontier, which is the post-quantum technique can help the design of quantum protocols such as test of quantumness and certifiable randomness generation. So this is quite counterintuitive because the goal of post-quantum cryptography is to defeat, say, quantum computers in some sense. But this picture is not completely true. So we can also show that post-quantum cryptography, the techniques can be also useful to design better and more efficient quantum protocols. And this direction has been explored in, say, these recent, say, 1 or 2 years. So it is very fairly new, and I'm very into this direction, and I will explore more. And after I have some results, and more results, I will definitely be happy to talk about them like with you. All right. So here is I conclude my presentation, and it's 2:01. So now it's the question time.
Thanks, Feng-Hao. Unfortunately, we have to turn it off because we want to be mindful of everybody's time. If you have any questions, however, we'll give you a few minutes to type those in the Q&A button at the bottom, and we'll ask Dr. Liu to answer those offline after our presentation here. And we will post the answers on our website at DOR FAU Research in Action. So thank you very much, Dr. Liu. Again, feel free to send us your questions. Have a great day. Bye-bye.